Thank you for your introduction, and I will start my presentation. Good morning, everyone. My name is Chanjo, and I'm majoring in robotics and mechatronics engineering at DIGIS. I'm very honored to present my study topic on optical interferometer-based force sensor system for enhancing precision in epidural injection procedure. Here are the contents of my talk. My study is related to needle-based intervention procedures. The intervention procedure is a non-surgical treatment for a condition that otherwise requires a surgical treatment. This procedure involves accurately pushing a needle or surgical tool at the target location using a guide system. A representative example of an intervention procedure is the pain intervention procedure. The chronic low back pain is joint among the elderly patients, and with a globally increase in aging population, the number of the patient is expected to rise further. Furthermore, the number of the related consultation and its healthcare costs are also increased yearly. To treat this, the epidural injection procedure is performed to inject the medication at the epidural space. Most important anatomical structures involved in this procedure are illustrated in this figure, including ligament flavum and spinal cord, and the space between them is called epidural space. The interventionalist must puncture the ligament flavum using a needle and immediately stop it to prevent the spinal cord injuries. In this process, they use the loss of resistance technique, and in the loss of resistance technique, the positive pressure is applied to maximize the resistance to belt. And as shown in this plot, once the needle punctures the ligament flavum, the resistance is disappeared. Based on this, they realize the needle is penetrated into the epidural space. And the Sion-based fluoroscopic guidance also the major approach to confirm the position of the needle. In the epidural injection procedure, interventionalists take the Sion images for each time, and based on the clinical margin, they estimate the depth of the needle during the procedure. However, performing the procedure very close proximity to the Sion, which emits in a radiation, possess the potential risk. In general hospital, interventionalists perform an average 4 procedure sessions per week. And each session lasts about 4 to 5 hours, meaning they are exposed to radiation for a significant amount of time. Therefore, the research is needed on the teleoperated needle positioning robot system. And this kind of robots requires an alternative sensor system for needle guidance. In particular, fiber optic-based sensors are gaining attention for their high accuracy and sensitivities. Additionally, due to their flexibility and small size, it is very suitable for the application of microsurgical needles. To measure the contact force or the pressure, the 2 types of interferometric sensors, fiber break ratings and peripheral interferometer, has been commonly suggested. My system, based on the peripheral interferometer, can measure the contact force directly between the biological tissue and the surgical needles. As shown in this figure, the fiber peripheral interferometer can implement it to compose the very small space between the optical fiber and the reflector. This is called epic cavity, and peripheral interferometer can measure the nanometric displacement of the epic cavity. From the characteristic of the interferometric signal from the peripheral interferometer, we can observe that the displacement of the epic cavity can be identified based on the spectral shift of the interference signal. Therefore, the whole system configuration for measuring the contact force can be illustrated like this figure. To quantify the spectral shift of the peripheral interferometer in response to the contact force, we calculated the phase shift using a signal processing. Additionally, the fiber peripheral interferometer was embedded into the inner canal of the 22-gauge interferometer. This design allows the system can directly measure the contact force and the middle tape. From the pilot study, we can observe that the phase shift is sequentially increased in response to the contact force. To validate the system's performance, we conduct the calibration process between the force and phase shift. Using a balance, we apply the actual contact force to the sensorized needle was incremented and approximately 0.1 during intervals. Based on this setup, we confirm that the linear relationship exists between the actual force and the phase shift of the sensorized needle. Now, I will introduce the user study to evaluate the system's performance. The user study was carried out over 4 days with the anesthesiologist at Seoul as a medical center. The aim of this experiment is detect the puncture of the ligament phlegm and position the needle at the epidural space. As shown in this figure, the needle penetration process is performed according to the actual epidural injection procedure process to the customized spinal phantom. And this spinal phantom has the 3 main sections: supraspinous tissue, ligament flavum, and epidural space. Total 23 interventionalists are participating in the user study, and during the study, the force curve was recorded according to the needle penetration process. The user study result from the force curve is depicted in the slide. The contact force began to increase the moment of the system made contact with the outer layer of the phantom, and 2 main drops in contact force are observed. In particular, the second drop is related to the puncture of the target layer ligament flavum. During the user study, the participants are recognized the puncture-related curve in the user interface, and they immediately stop the needle within the epidural space. To further confirm that our proposed system is sufficiently safe in the epidural injection procedure, we measure the invasive depth of the needle and its test success rate. Clinically, the maximum size of the accessible epidural space is approximately 5 millimeters, which we defined as a safety margin in the user study. Any penetration beyond this safety margin is recorded as a test failure. Although the participation of the interventionalists with the wide range of clinical experience, the user study demonstrated that the mean invasive depth of the needle is 3.24 millimeters, and the success rate is 72.63% using a proposed system. Through the user study, we successfully presented the quantitative performance of the system. Finally, I will introduce the ongoing study related to the robot-assisted injection system. As shown in this figure, the epidural injection system drives the sensorized needle using a linear actuator. And epidural injection system drives in two modes. The contact force tracking mode, maintaining the contact force with the ligament flavum with the predefined contact force, and target layer puncture mode. We conducted the penetration test on the spinal phantom using a straightforward feedback control loop. According to the result, in the tracking mode, epidural injection system maintaining a contact force with the ligament flavum, and in puncture mode, we can observe that the sudden drop in the contact force because of due to the ligament flavum puncture. As summary, we developed an optical force sensor based on the peripheral interferometer. We conducted the user study to evaluate the test successfully and the needless invasive depth. In both cases, the mean invasive depth was under 5 millimeters, and an average success rate of puncture detection test is 72.63%. As a future work, we plan to implement an adaptive control algorithm for automated robot-assisted injection. Furthermore, this system is anticipated to be applied various microsurgeries requiring a precise force measurement. And this work was supported by the Administration of the Trade of the Korea. So, as far my end of my presentation, thank you for listening.
Thank you, Chan. Are there any questions? We have time, don't have time, very quick one, very short answer.